Okay, in this class I want to talk about uh, connecting really contingency tables and Venn diagrams. Before I get to contingency tables and Venn diagrams, I want to just remind you of what complementary events are. So two events are said to be complementary when one event occurs if and only if the other event does not. So we're talking about two events, and those two events have to cover all the possible outcomes from some experiment. So if I flip a coin, and I define event A as the coin lands heads up, event A complement has to be the coin does not land heads up. So they cover all possible outcomes from that experiment. If event A is I win the race, well, event A complement will be I do not win the race. They cover all possible outcomes in that experiment. If event A is my cow gets hit with a banjo, event A complement is my cow does not get hit with a banjo. They cover all possible outcomes. There are no other things that can happen to my cow. Either it will be hit with a banjo or it will not be hit with a banjo. We have the complement rule for any event A, which says the probability of any event added to the probability of its complement has to equal to 1, because the two events, A and its complement, cover all possible outcomes in an experiment. So together, one of them is certain to happen. Either the coin will land heads up or it will not land heads up. Either I win the race or I do not. Either my cow gets hit or it does not. There are no other things that can happen, so the sum of those probabilities is 1, which gives us a nice rule for finding the probability of the complement of event. We subtract the probability of the event from 1. So I'm going to get into this thing on Venn diagrams, and you'll remember seeing these things before. This diagram shows the number of outcomes in each region of a sample space for two events A and B. I'm going to think about, how many things are in this, how many outcomes are there altogether. Well, 3 and 6 is 9, 9 and 2 is 11, 11 and 9 is 20. To draw the corresponding contingency table, a few vertical lines, a few horizontal lines. Put in your events. A, always if A is one row, then A complement is the other row. And then we sum them up. Notice when we add events A and A complement, their total sum has to cover, I should say, we're not talking about probabilities here, has to cover all possible outcomes. So there's 20 possible outcomes here. We also have event B and B complement. The first two things I'm going to jump on there's the intersection A, it's in A and in B, there's two things in there. And then I'm taking this thing out here. It's outside A and outside B, that's 3. And then 6 is inside A, but outside B. 9 are inside B, but outside A. So altogether there's 11 outcomes in event B. There are 9 outcomes that make up event B complement. There are 8 outcomes that make up event A, and there are 12 outcomes that make up event A complement. Should put that in there. To find the probability of A union B complement, well, A union B complement means it's outside A. It's not in A or B. A union B means A or B. A union B complement means neither A nor B. So it's not in A and not in B. That's where you'll find that information. Remember, the total number of possible outcomes in this experiment is 20, and 3 of those outcomes make up A union B complement. So the probability of A union B complement is 3 over 20, which would mean the probability of A union B has to be 17 over 20. Because together, this event, A union B, and this event, its complement, have to add up to 1. Okay. The other way, of course, is to use the addition rule, which says add up all the ways you can get A, add up all the ways you can get B, and then subtract the double count. So 11 plus 8, subtract 2, giving me 17, divided by a total of 20. Let me look at another example. Here's a contingency table showing the number of outcomes in each region of a sample space for two events A and B. I want to complete it. Remember, these are sums, so 30 plus this thing has to be 100, so that has to be 70. This has to be 60 because it must add to 40 to give me 100. This has to be 50 since it has to add to 10 to give me 60. This must be 20 since it must add to 50 to give me 70. And finally this must be 20 because it must add to this 20 to give me 40. A union B complement, I know, is that cell. Let's draw the corresponding Venn diagram. Loop for A, loop for B. They are intersecting because there is a crossover in there. That 10 elements in both events. Outside here, that's 20. That 20 here in this cell corresponds to that 20 there. Inside A but outside B, well, I'm in row A but in column not B, that's 20. Inside B but outside A, well, I'm in column B but in row not A, well, that has to be 50. The probability of A union B complement, well, the total number of possible outcomes is 100. There are 20 elements that are in neither A nor B. And A union B means in A or B, so in A union B complements means neither A nor B. That's 20 out of 100, 0.2. Which means the probability of A union B has to be, well, 0.8, because together those two complementary events, their probabilities have to add up to 1. I could also use my addition rule for probability too. My addition rule says the probability of A union B is always the probability of A added to the probability of B, subtract the probability of A intersection B. So in other words, we count everything in A. Try a different color there. Everything in A. And then we count everything in B. But then we have to be careful because we've got to remove that double count in there. So, probability of A plus the probability of B minus the probability of A intersection B. Altogether, total number of possible outcomes of 100. Everything in A, well, that's 30. Everything in B, well, there are 60. But we'll have counted that 10 twice, so we got to remove that at the end to give me 80 out of 100. Probably a bit quicker though to find the complement first and then subtract from 1. Let me look at another example here, completing the Venn diagram showing the probabilities in each region of a sample space. So now we're showing probabilities instead of the numbers of outcomes, and we know that the sum of all probabilities in any experiment is equal to 1. So all these numbers have to add up to 1. 0.1 plus 0.4 plus 0.2, well, that gives me 0.7, so that has to be 0.3. To draw my contingency table, a few vertical lines, a few horizontal lines, A complement, total sum, B complement, total sum, and just fill everything in. I'm going to start by looking at the intersection, which is 0.2, and the complement of the union, which is 0.1. And after that, then, I'll look at in A but not in B, inside row A but in row not B, that's 0.4. And then I'll look at in B but not in A, in column B but in row not A, that's 0.3. And now I'm ready to add everything up. 0.2, 0.3, 0.5, 0.4, 0.1, also 0.5. Notice everything has to add up to 1. 0.2 plus 0.4 is 0.6. 0.3 plus 0.1, 0.4. That's my contingency table. Notice strong links between that and my Venn diagram. I think your contingency table gives you a bit more information. Gives you 9 cells worth of information. In fact, this gives you 1, 2, 3, 4 cells worth. The probability of A union B complement. Well, the easiest way to find that is just to look in that cell, which corresponds with this number. That's equal to 0.1, which means the probability of A union B has to be 0.9. I could have also found my addition rule for the probability of A union B. It's the probability of A, 0.5, plus the probability of B, probability of A, 0.6, plus the probability of B, 0.5, subtract the double count, 0.2. You'll also get 0.9. One final example here, again, just some probabilities in a contingency table. We're going to complete the contingency table and draw the corresponding Venn diagram. 0.1 plus 0.3, that has to be 0.4. 0.1 plus something is 0.4. Pretty straightforward, that has to be 0.3. The key detail here is the sum of all the probabilities in any experiment have to be equal to 1. This is showing probabilities. From here we can figure out that has to be 0.6 because together they have to add to 1. This also has to be 0.6 because together these have to add to 1, which means that must be 0.3. Check all your addition along each row, check all your addition along each column, make sure everything adds up. Venn diagram, box with 2 loops, events A and B, sample space, the sum of all the probabilities in a sample space must be 1. And again, I'm going to focus in on this 0.1, that's the intersection. I'm going to focus in on this 0.3, that's the complement of the union. And then I'm going to look at in A but not in B, that's 0.3. And then finally in B but not in A, that's 0.3 out there. I want to find the probability of A union B complement, and I'm hoping you know exactly where to look. It's in this cell or it's out here. It's 0.3. To find the probability of the union, or the probability of the union is just, well, it has to be 0.7 because together this event and its complement have to equal to 1. Their probabilities have to equal to 1. How else could I get it? 0.3 plus 0.1 plus 0.3 giving me 7. Or add up all the probabilities in row A, that's 0.4. Try that again. 0.4. Then add up all the probabilities in column B. That's also 0.4. But I'll have counted these ones twice, so I'll have to remove 0.1, and that gives me 0.7. Exactly the same as that. Okay? But ultimately, you know, the big thing is to understand the connection between contingency tables and Venn diagrams. Remember, complementary events, the sum of the probabilities of complementary events is always equal to 1. What are complementary events? Well, 2 events are complementary. Let me put the definition up again. When one event occurs if and only if the other does not. Okay, thank you.